Do you speak my language? Today's presentation is about static analysis tools, how we can make them communicate with each other, enabling security teams to have a deeper understanding of their attack surface and allowing them to identify complex vulnerabilities. To set the scene for this talk, I would like to show you 3 code snippets of increasing complexity. The first one here is the simplest. In one function, we take user input, create a query, and then execute that as a MySQL query. As we all know, there is a SQL injection vulnerability here. But because everything happens in one function, it's easy to solve this problem with linters, grib, and other tools. We won't be spending too much time speaking about this problem. In real code, you often have wrappers, abstractions, and frameworks that would make the call graph more complex. This code here is vulnerable to the same SQL injection vulnerability, but in order to find this vulnerability here, you would need taint flow analysis. There are open source tools from Facebook and other companies that would help you to solve this problem. We'll briefly talk about taint flow analysis in this presentation to get the basic information and the background information that we need for our next example. Our presentation mainly is about this code here. Note, in the left-hand side, we have PHP code, and on the right-hand side, we have Python code. This code is also vulnerable to the SQL injection vulnerability. The code on the PHP, on the left-hand side, starts as the previous example, but then we do an RBC call to fetch data, which takes us to the Python code that have a SQL injection vulnerability. The SQL injection vulnerability exists, but in 2 different code bases. I'm Ibrahim Mohammed, and today we'll be speaking about cross-repo taint flow analysis. Before we dive into the presentation, let me introduce myself. I'm a security engineer in the Facebook application security team. I've been working for Facebook for around 5 years. I focus on detecting security vulnerabilities, doing manual code review to detect security vulnerabilities, but I also like to spend a lot of time with software engineers to see how can we automate the detection of these security vulnerabilities. Over the past 5 years, I've been working on Zonkolan and Pisa. Both are static analysis tool for PHP and Python. Before Facebook, I used to work as a security consultant, mostly focusing on penetration testing, red team exercises, and also code reviews. With me out of the way, let's talk about our agenda for today. So we'll first start with the motivation. Basically, we'll talk about how common is this SQL injection example, how common this code pattern here, and then we will go into single repo analysis. We'll take that SQL injection that lives in one code base and see how can we find this with taint flow analysis. In this section, we'll try to get the background information for the section after, cross-repo taint flow analysis, which we will dive deep into taint flow analysis, how we can find that SQL injection between 2 different code bases. And then to the example flow, which is my favorite section here, because we will show you a real vulnerability that we have found with cross-repo analysis and showing you the real impact here. And then I would like to end up with looking forward, how I see this moving over time, and sharing some thoughts and ideas. Now, let's start with the SQL injection example. Probably when you have seen this code, you either think of like, is this common? How common is this in code bases? Or the other idea is like, yeah, I have seen this in our code base. I've seen this. We are doing this all over the place. But to give you more background and context about this, usually when you build system, you start with something like this. So you have one monolithic code base has more of your application logic that connects with one database to read and retrieve data. But sooner or later, we realize that there are a couple of problems here. One, this is not very scalable. Also, might have not the best performance. And then you will start to move into that direction here. So you have your application logic, and you have different services that communicate with your application logic. Previously, these were part of your application logic, but now your application logic is less in code and you have different dedicated services. This approach is becoming more popular because you can take the service, scale it, you can write the service, let's say the authentication service, you can write this in C or C++, which is more performant than what language that you use in your application logic. And to take as an example, so we have Twitter here. This is a slide from Twitter around 2014. You can see one monolithic code base connecting to the database to store and retrieve data, which is normal and natural to do in the beginning of your system before like very kind of hard scaling limitations. But then we see Twitter evolving to that design here. A lot of services communicating with each other, and again, this is normal as you scale. Another example is Netflix. Again, initially you start with one monolithic code base, one monolithic database, but then you see them evolving into something like this, a lot of services communicating with each other. So that SQL injection, or that vulnerabilities that exist between different code bases, they are there because You have now your application connecting with services, but just the vulnerability lives between these services. It's deeper in your attack surface, but they do exist. In our case, in our demo example, we have an application logic written in PHP and our backend service written in Python, and the SQL injection is split between both. Another case why cross-repo is important is scalability. So in Facebook, we know that it's difficult to review code manually. As security engineers, you don't have a lot of security engineers comparing to the software engineer teams that you have, so we need automation. And we rely heavily on static analysis. So we usually follow this strategy here. You have your code base, analyze this with static analysis. Security engineers review the results and identify valid vulnerabilities. This scales up very well, and we will see that. And also you can take this, apply it to different products. It also scales, and it enables us to scale our security team. But when you draw the full picture, you have something like this. So you have your user-facing applications connecting with backend services. What do you do with the backend services? Do we run static analysis without any information about their attack surface from user-facing application? If we do that, the noise will be high, and we won't be able to tackle that noisy issues, and we won't have a good idea of which vulnerabilities are exploitable, reachable from outside, versus which ones are only internally reachable or even not reachable at all because there are no service that is calling that. And also we know that we cannot manually review these backend services because they are a lot. It's not the way to scale. So with cross-repo analysis, we are able to find the full path, the full attack surface until we hit the service, which helps us a lot with scaling. Now let's jump into static analysis. Static analysis is one of the worlds that can be easily overloaded. It can mean different things. Running grep on files is called static analysis. Linters are called static analysis. But what do we mean by static analysis here is taint flow analysis. And if you don't know what taint flow analysis means, that is fine, because this is what I'm going to show you next. So let's go back to our single repo example here, SQL injection. So we know there is a SQL injection here, and in order for me to show you how taint flow analysis can find that SQL injection, let's follow this approach. Let's find the vulnerability with manual code review manually, and then see how a taint flow analysis tool will find this vulnerability for us. So manually, what you would do, you will start reviewing code. So you will start from wrap get page name. You will realize it calls the get page name, and then you will go into get page name. You realize it calls the request, and once you go into that, you also realize that it calls returns the superglobal PHP request. So you know that superglobal the request, which is a user-controlled input, goes back to get page name and returns to the wrap get page name. You will take that information and then review the second function, which is wrap fetch data. You go there, it takes the arguments, call fetch data, and then you go one step deeper. It also it takes the argument, concatenate this with a string, and it calls MySQL query. As a security engineer or a security consultant, you will realize that, okay, there is probably a SQL injection vulnerability here. MySQL query is not SQL safe if there's no validation or data sanitization happens. And because we have user-controlled input from wrap get page name to wrap fetch data, then that is a SQL injection. Now, let's put the taint flow static analysis hat on and see how can we detect this with taint flow analysis, or how a taint flow analysis tool should work. So it will work more or less the same. So the tool will start from the wrap get page name and try to analyze this function. But to give you a good understanding of how it works, let's start from the deepest call, or the request function. So when the taint flow analysis tool analyzes this function, it will say this function is returning a user-controlled source. So what is a source? So a source is a function or a method that return tainted data, or data that the taint flow analysis tool want to track across the call graph. The taint flow analysis tool want to see where this data is going. So here we're marking the return of this request as user-controlled source. This is the initial configuration that we give the tool. So the tool knows that, okay, this is returning user-controlled source. It will also analyze get page name, which also return the result from request, which also user-controlled source. We'll do the same with the wrap get page name, and then now the tools know that X is coming from a user-controlled source. Now, the taint flow analysis will analyze wrap fetch data, which realizes that fetch data passes the argument into MySQL query, and MySQL query will be provided in the configuration as a SQL isync. So what is a sync? A sync is a function that we want to see any tainted data that flow into that function. Whenever there is tainted data that flows into that function, we want to create an issue, or we want to highlight that flow. So the MySQL query is our initial configuration, and then the taint flow analysis tool knows that fetch data leads to a SQL sync, and also know that wrap fetch data leads also to a SQL sync. And now with these two combined, we will have a rule that says if you have a source coming from user-controlled, and that flowing into a sink of type SQLi, then that is a potential SQL injection vulnerability. To see everything in one slide, you have the trace here. So a trace is how the data is flowing between a source to a sink. We start from the bottom left, request, return a source, which forward that to get page name, which forwards that to wrap get page name, and in the root get response, we take that argument, pass it down until we hit our sink, the MySQL query sink here. With this technology, we were able to create 3 tools that does exactly the same. ZoneClan, a taint flow analysis tool for Hack. It analyzes Facebook.com, Oculus.com, and other websites that are powered by Hack. I think ZoneClan analyzes around 100 million lines of code in our code base. PISA is our static analysis tool for Python. It's open source, it is free, and we use this to scan and protect Instagram.com. Mariana Trench, which is our recently open source taint flow analysis tool for Java and Android code. We use Mariana Trench to analyze our mobile application and our Java backend services. These 3 static analysis tools rely on the same technology that I've just explained to you. To see how these work and what's kind of when do they work, let's look at this kind of architecture diagram. So security engineers define sources, sinks, and rules for every tool. Depending on the code base, we run the correct tool. So PHP, we run ZoneClan. Python, we run PISA. Java, we run Mariana Trench. We analyze the code, store the result into the database for later consumption or triage by security engineers. And with that, we were able to find 50% of total vulnerabilities that we found through automation. So 50% of all the security vulnerabilities that we found from white hat, from manual code reviews, 50% of that number came from automation. Automation includes static analysis and dynamic analysis, but a big portion of that came from static analysis and from the tools that I've just explained to you. Now, with single-repo analysis out of the way, let's jump into the main topic, or the cross-repo taint flow analysis. Let's go to that SQL injection and how we can find that SQL injection across 2 code bases with taint flow analysis. We'll follow the same approach. We will start off with doing this with manual code review, and then see how a taint flow analysis tool will find this for us. So with manual code review, you will probably start from the PHP side. We know how it starts from the previous example, but then you will realize that there is a socket, you're creating a HTTP client, you're calling some service and you're fetching data, and then sooner you realize that this is thrift. So as you're reading the code as a security engineer, you will realize that this is a thrift call. What is a thrift? Thrift is a lightweight language-independent software stack for point-to-point RPC implementation. So thrift, you can think of it as an abstraction that would allow software engineers to define a service that says, I have a service that is exporting this API, write this in an interface language, and then thrift will auto-generate code for all clients to connect to that service, and it will create stubs for how the server should be implemented. So that code here, it's auto-generated code, or like the page service async client. This client is auto-generated code, and we use this internally to be able to have this RPC connections between services and client. So after you gain that knowledge, and notice this is an extra overhead for security engineers, which is a very manual process, which is part of the manual review, and it would be great if we can make static analysis aware and familiar with that. So once you do this, you would want probably to know, okay, what is the service that I'm calling, and you realize it's page service from the client class page service async client. So to sum this up, you have 2 flows. One here is coming from the request, so the user, the data coming from user controlled, and then flowing into a call to a thrift service. Now, with that, we jump into the other part, which is the server implementation. It is implemented in Python here. Again, I know there's a lot of code, but it's part of thrift being aware of that. Well, let's focus on the function that we care about, fetch data. This is very simple. It takes an argument, construct a query, and execute that query as a SQL query from the cursor execute. From a manual code review perspective, you take the argument which you know from PHP is user controlled, and then you go into cursor execute, which also, you know that if there's no data validation or sanitization, this will lead to a SQL injection. Now, with both in mind, so you know there's the PHP part that is user controlled, that is calling the service, and here is the implementation of that service. You have your SQL injection with manual code review. So if we were to find this with taint flow analysis, you probably want something like this. So if I have a PHP static analysis tool that can review the code and can understand that this is a call to a thrift service, we can probably use ZoneClan for that. And then if I have a Python static analysis tool that can review the code and also identify that this function is a thrift service implementation. We can use PISA for that and somehow make these tools connect to each other. And the zone client says, hey, PISA, I know that someone that is user-controlled input or untrusted input going to this service. And then PISA says, oh, and this also is going to a SQL injection. Let's see that in action. So the wrap get page name. So let's put the taint flow analysis tool and see how the taint flow analysis tool will, or zone client will analyze this code base. So it will start usually with analyzing the code normally. So it analyzes this code, but then it also realized that, okay, there is a thrift call here. So we want to mark all thrift calls as sinks. Whenever we're calling a thrift service, you want to mark this as a sink. So we map all user controlled input to that thrift service. And once you do this, we call this the producer run. So the zone client is running and identifying flows from user input to these services in a producer run. And you want to store, we call also this a partial flow because the flow is not leading to a real sink, it's leading to that kind of intermediate sink, which is the thrift RPC. You want to have this information and then store it into a database. So we see here, we're storing this data, which here the information, external user controlled input, going to page service fetch data. Notice here that we are not using the page service async client or the page service client. We're using the canonical name of the service and not the actual client name that is auto-generated from thrift. Once you do this, let's go to the Python part. So Python, the first thing that you want your static analysis tool to be familiar with, that this is a thrift implementation, or this is the implementation of my thrift call. So once the tool knows this, and this is before the analysis, the tool will need to look up that database and see, okay, do I have any information that I need to be aware of before my analysis? And so the tool will look up with the canonical name, it figure out the canonical name, and then it will look up into the database. We realize that zone client have actually stored some data there for the tool to be used before the analysis. So the tool will take that information, augment its initial model. So now before the analysis, I will augment that information. I will keep in mind that zone client told me that there is user-controlled input here, and then I will just analyze normally, and eventually you will be able to find that SQL injection. The coming two slides they have a lot of information, but I'll try to abstract as much as I can, but I would really like to show you or give you a sense of what goes under the hood for these two tools. So here is the model or the taint summary from zone client. You see here we have external user controlled input coming from a wrap get page name and flowing to the page service async client fetch data, which is marked as a sink here. Notice that the service name or the sink name is the actual service async client, not the canonical name. And then what we want to do is take that and then create the kind of partial flow from that. So we replace the name with the canonical name, page service fetch data, and source, and then we store that into a database. So this is just, this box here is the same as this box, but here stored as a row in the database. Now, on the Python side, this is the summary before anything, which is empty. We don't know anything. And what you want the static analysis tool to know that, okay, this is a thrift implementation. Let me look up that database. So it looks up the database. It finds information coming from zone client, which is the producer. And this is the consumer run, or the run that will use the data from the producer before the analysis. So, and it augments these models. Again, before the analysis, we augment this model with external user controlled coming from zone client, and then start analyzing that Python code. And after analyzing that Python code, then you see here we are going to this you have the full taint flow. We have external user controlled going to the SQL injection. And now we have the SQL injection vulnerability between two different code bases with taint flow analysis. To see everything in one slide, let's see our trace. So the trace starts like similar to the previous example. We start from request, top left corner. On the left-hand side, we see the PHP part. On the right-hand side, we see the Python part. The root here is the canonical name of the service and the function name. So this is like the canonical connection point. And you see here the mangling and demangling of the service name. So in the PHP, the client called page service async client, and on the right side is the page service handler, which is the implementation for that service. And yeah, just the data flows from here to the service, and then from the service back into the sync function here. So to recap, if you want to do or to have like cross-repo taint flow analysis between taint analysis tools, the first thing is that you want to mark your all RPC calls as sinks. In our case, this was FB thrift calls, so we want to mark these as sinks so we can find the flows between user control to these sinks. And then you want to define canonical connection points. So given a service, from the server implementation class or the actual implementation, how can I go to the canonical connection point of that service, and from the client call, how can I find that canonical connection point? Because this canonical connection point is important, because this is how you're going to store your data intermediately between these services, and you'll be able to look up this data. And then you want your engines to be able to find the flows from user control input to the thrift call, which we call them the partial flows, and this is in the producer run. And then once the consumer engine or the other engine that's augmenting its initial model with that, it can load this partial model and then start the analysis from there. And last thing, you want to make sure that you store this data in a format that you're able to visualize the entire flow seamlessly across code bases, which is very important, so security engineers and software engineers can act on that. Let's go back to our design diagram. So it used to look something like this before cross-repo taint flow analysis, but after cross-repo taint flow analysis, it looks like this. I know it is a lot here to take in, so let's break it apart. This is the producer run, zone clan, running in PHP. We have security engineer defining sources and sinks. Remember, now we have the sinks also as our RPC calls. So zone clan analyzes PHP, stores the result in the database normally, but we have an extra step of extracting these partial model and storing them into a database that we call crtech, and we will define in coming slides. And then now on the consumer run, PISA, before the analysis, it will look up the crtech to augment any initial model for thrift implementation. We'll do the analysis normally, store everything in the database, and security engineers can see the entire flow there. So what is crtech? crtech is a tool-independent store of taint information in a tool-agnostic format. So we want these tools to use that crtech or an abstraction on top of DB to store taint information, to push and pull taint informations. These information are tool agnostic, so Zoom Client can push model, PISA can pull that model and reuse it in its analysis. Now, let's see how can we view the traces. It's important to view the traces seamlessly, so you can abstract all the complexities in between and all the overhead between of the thrift services or these connection points for security engineers. For single repo analysis, viewing the traces is straightforward. You start with the root and then you expand the traces to the source leaf and to the sink leaf. So you start at the root and then you go here, drop, traverse until you hit your sink leaf, and then you go here until you hit your source leaf. For cross-repo analysis, theoretically you want to do the same, but there are a couple of differences. One is the actual flow under the hood looks something like this: source to a sink thrift call, and then from the thrift implementation to your sink. This is one difference. The other difference is that these, if you notice that like the one on the left and the one on the right are actually two different systems, ZoneClan and PISA. Yes, it happened that we created them at Facebook, but they are two different systems. They can be in two different databases and they have their own different tables. So you want to have some meta information of when you reach that root, how can you go to the other part. So in order to view the cross-repo traces, you start from the right-hand side, which is the flow from the service implementation to the sink. So you start from here, you expand the trace until you hit the sink leaf. You also expand until you hit the source leaf. Your source leaf is the thrift implementation or that canonical connection point. Once you hit that canonical connection point, you go to the crtech to find who are the producers or who are the other engines that are storing data into my run. And then once you go there, you go into the database from crtech, switch to the right DB, switch to the right tool, take that information, and then you expand the trace normally backward until you hit the source leaf. And this is how you get like from the user input to the thrift call, and then from the thrift implementation to the actual sink, your SQL sink. Now we know how we find SQL injection single repo, how we find SQL injection cross repo. How does this work so we can actually find true bugs? How this is deployed at Facebook so we can find true vulnerabilities. So we start with like configuring our producer runs. So usually you want your producer runs to map all your attack surface. You remember that picture we're showing, we have user-facing applications. So you want all your engines to be working on this user-facing applications to map all the attack surface. So we have ZoneClan analyzing Facebook, PISA analyzing Instagram, Android application analyzing our Mariana Trench analyzing all our mobile applications. You might be wondering, why do we need to analyze the mobile application and know what are the entry points to our backend if we will mark everything on the backend as user controlled? Like if you mark all entry points on your web tier, why do you need the mobile application? I will show you in a couple of slides why this is important. Now our consumers, we mentioned that we use FP-thrift and rely heavily on FP-thrift. So anything that relies on FP-thrift, we analyze this. You have implementation in PHP, Python, and Java. All right, how regularly do we run? So now we know how these are configured. So we have, we run on all the code, like when it lands or when it's pushed. We run there, which we call it the master run. It's usually multiple times a day, and for any new findings, we file a task. But we actually also want to do better than that. We don't want to wait for the vulnerability to be pushed or for the code to land. We want to catch it before this. So we have another mode, which is the pull request mode. So with every pull request that engineer creates, we review the code before that pull request and after that pull request, and we see if there is any new vulnerabilities. Any new vulnerabilities, we attribute it to that pull request. If we are confident about the vulnerability, we automatically comment in the code to prevent this from landing, and we provide guidance to the engineers to prevent that SQL injection or RCE. But if we're not very confident from the vulnerability, we loop in the security engineers to ask them to triage that vulnerability for us. Now to the most favorite part for me, the actual vulnerability that we found, or an example of an actual vulnerability we have found. Two things I would like to mention. One, because it's cross-repo flows, so they are expected to be slightly complex, so I apologize in advance for this. I'll try to do my best to abstract the code for you. The other thing is that this vulnerability was found in a testing environment, as in the code landed and everything, but the code was only enabled for the development team. This did not affect any real users, no one real user has been affected by this. So let me start with giving you an overview of the vulnerability. So one, it is a remote command execution. Yes, we have found a remote command execution was cross-repo analysis, which for me is like amazing. All right, so the flow starts from workplace and ends in a Python service. So workplace, if you're not familiar with workplace, is something very similar to Facebook, but it's for companies to be able to communicate and collaborate. So for employees inside companies to be able to communicate or collaborate. We actually use workplace internally. And workplace has a feature. So workplace is written in PHP. So it's being analyzed by Zonkla, and it has a feature for video call rooms, or so you can create a virtual room where you video call with your coworkers and your teammates, and that service has parts of it that was written in Python, and the remote command execution were in that Python service, but you're in like the application that is part of your attack surface is workplace. Now let's go one step deeper. Let's look at our trace. This is our trace here. I know it's a lot to take in, but let's break it apart. The left-hand side is the PHP part, your kind of initial attack surface, or your entry point for the attack surface, and we will start reviewing the code from here or seeing the code from here. The right-hand side is the Python part. Again, we will dive into this deeper. Two things I want to highlight here. One, this is the canonical name for the service, as we have seen in the demo example. This is the canonical name, is the root of the tree, but also here also is this is the producer run ID, which I've mentioned earlier. It is important to be able to get that meta information when you're viewing the trace seamlessly. Now, let's dive deeper more. So from the code, let's start with the PHP part. So as you can see here, this is a GraphQL mutation root field. If you're not very familiar with GraphQL, so GraphQL, you can think of it as a REST API that our mobile applications use to connect to the server. So from a security engineer perspective, this is your entry point or part of your attack surface. So the argument data here is user controlled. So what we do is that we take data and we forward this to the gen-spawn function. One thing to highlight here, this is the check that made sure that this code is only enabled for the development team. Now let's go one step deeper inside the gen-spawn. So gen-spawn takes the route, which we know is user controlled from the previous frame, and then creates a request and calls the client start. Very similar to our example demo where you have like service name and then start. So here we're calling the start function on some service, and the request object is user controlled or contain tainted information. Now this is the last frame before we jump into the Python part. So now we will jump into the Python part. Here is the definition of that function, or the implementation of the start function. Request is user controlled, or contains user data, contains tainted data, and we take request and we forward that into start async. Inside start async, the request, we access the route member from that, which is also user controlled input. We create the args variable, which we later use that also with some string interpolation to create the exit command and eventually called the vmexec. Last frame in our vulnerability here is the vmexec. We take the command and then we call ssh client exit command. The ssh client is a client class in the Paramiko library. Paramiko is a Python third-party library that allows you to ssh into machine and execute command. If the command object contain untrusted input, you can have a command injection vulnerability here, and this is what we have here. So the entire flow, starting from the PHP part, going into the Python part, and eventually leading to a remote command execution from the exit command called of Paramiko. RCE in 2021, yes, we managed to find this, and we managed to find this with cross-repo taint flow analysis. No manual review being done to find this. Just the tools saying this is a potential RCE here, to triage it, and yes, it is a potential RCE. It's very difficult to find RCEs, and with our tooling we were able to find this, and we were able to find this in a testing environment before it lands and affect any of our users or our products. There is a lot of challenges and improvements to take this from here to and keep improving on this. One of the challenges that we want to work on is false positives or a bad signal to noise ratio because of some sanitization happening in one path. So one in PHP or in the Python, some sanitization happening in these two paths. When we send this information across CRTech, or when we send this taint information, we don't necessarily send, oh, there's a validation here. We just send there's user input going to the sink here. But if there's int casting or enum casting, that can lead to bad signal to noise ratio, and we're actually working on this improvement. There's also the creation points for FP Thrift. We want to make it easier for anyone to create extra connection points. So how you can support gRPC, how can you support Apache Thrift, or any other tools similar to FP Thrift, or even how can you support normal HTTP calls that the implementation in a Django application or Flask application inside your environment. Also, as you see in the real example that we have shared with you, the trace is slightly complex, and this is expected because the cross-repo flows, but it would be great if we can come up with some creative ways to make the flow simpler and simpler so that engineers can easily understand and act on that. Fix ownership. Who should fix that SQL injection? In the demo example, who should fix the RCE? Is it the service or the client calling the service? So sometimes, yes, the server's responsibility is to make sure that the service is self-sustained and like secure by itself, but also sometimes the vulnerability, if let's say missing permission checks, the client sometimes would need to perform these authorization checks before it calls the service. Looking forward, I see there are different ways where this can evolve over time. I'll start first with this direction here. So research to standardize the taint flow summaries. It would be great if we have more research around how the taint flow summaries can be tool agnostic, can be standardized, and can represent everything. It would be great for PISA to be able to communicate with CodeQL, with RIPS, with other static analysis tools to build more complex ideas on top of that. The other idea is the mobile attack surface. So the mobile attack surface, if you think of that, you usually have your exported components and requests from backend. Exported components, how other applications on the same device communicate with your application, but requests from backend, how is your backend is communicating with your phone? Should you mark all the requests from your backend as potentially user controlled or like untrusted input, or should you mark everything coming from your backend as trusted input? Both have like pros and cons, but with cross-repo taint flow analysis, you will be able to find exactly and precisely what is coming from your backend that is user controlled input, and how does this affect your mobile application. Another improvement area that I can think of, backend storage, is most of the systems today, or most of the taint flow analysis systems today, if you have user control input going to a database and somewhere else in your code, you read that input from database and then you go to a val or some RCE sync, most of the taint flow analysis tool will not be able to find that vulnerability for you, because for them the backend is a black hole, or the backend, everything from the backend is tainted and untrusted, which very, very noisy. With cross-repo taint flow analysis, you will be able to see precisely what is that. This is an example here. So imagine we have a request, save image, you store an image with some name that is stored into the database, and then somewhere else in the code, another request or another endpoint that view an image with an ID, retrieves that from the database, the image, the content, and the name that you provided in the first request. There is a path traversal vulnerability here. most of the tools nowadays will not be able to detect this vulnerability, but with cross-repo taint flow analysis or the same mechanism, you will be able to know that whenever you're retrieving this data from the database, it was user tainted in the first request, and then you'll be able to see the entire flow, giving you kind of better view of your attack surface. Last idea for this to grow, which is one of my favorite, is privacy relevant flows. Imagine Mariana Trench working with ZoneClan or some of our backend analysis tool, where you can see a flow coming from a sensitive sensor, speaker, camera, GPS location, fingerprint. I know they mostly stay in the device, but imagine you have this ability where you see the data coming from the sensor. We're reading the data from the sensor. We're sending this data across our backend, and what we do with this data with our backend. So with cross-repo taint flow analysis, with Mariana Trench speaking with PISA or ZoneClan, you will be able to find that flow. You will be able to find flow leaving from a sensor, going to your backend, and what do you do with data at the backend. Takeaways. So if you're an application security engineer and application security teams, you probably know that there is a lot of code there. You have a lot to review. Use static analysis. It scales. It's scaled with us. We have great open source tools. They're free to use, and they have great documentation. You can go and try them right away. You have all the knowledge to build cross-repo taint flow analysis, so go and try it out. For security consultants, you might think it's like, I don't own code, I just do code reviews now and then. Maybe I don't need to use taint flow analysis. Yes and no. So if you have Python code or Java code, you can just get a quick head start by analyzing this with Python and Mariana. But what you really can use is, if you have a question like, what are all the ways that I can get an RC in Python, or what are all the ways that I can get SQL injection in Mariana Trench, we have our configuration open source. These have all the ways that an RCE can happen in Python. A SQL injection can happen in Java, and you can look at these configuration and get this knowledge quickly and know if this is a vulnerability, if this flow can lead a vulnerability or not. And if you find a new kind of API or something that can lead to an RCE, please feel free to share it with us on our configuration. And if you really want to see everything working in action, if you really want to see cross-repo taint flows working in action, feel free to join us at fb.com/careers. For static analysis researchers, all our static analysis tools are open source. Feel free to look at the code. Feel free to participate with any ideas or thoughts that you have in mind. Also, it would be great if you can spend more time researching about tool agnostic taint summaries. Last slide, which is the most important for me, is I would like to thank everyone whose name is here. They have played a very, very important role for the success of this presentation, and I hope really you liked it. Thank you, everyone. Thank you for your time, and I'm looking forward for your questions.